Civis is a two-pronged approach to analyzing and solving problems in engineering and other disciplines using simulation modeling techniques and visualization technologies. For instance, when you're working with heavy industry, there's a lot of processes that are very difficult to get instrumentation into. It's really hard to put a temperature probe or sensor inside of a blast furnace because you get down to the lower levels and you're burning fuel and coal and gas and all these things, right? And the temperatures will just melt equipment, right? So it's very hard to get measurements. Simulation modeling lets us use a computer to actually replicate the physics of what's going on in a system and then take the results from that simulation and use our new visualization technologies that have been exploding all over the world, right? And try and visualize what those simulation results look like. Virtual reality isolates you from the real world. You have headphones on, you're staring into a virtual environment, right? Augmented reality is not an isolation from the real world. It is overlaying virtual things, virtual models, virtual displays, heads-up displays, whatever, onto the real world, right? So if you think about like a heads-up display in your car that's overlaying your speedometer onto the like windscreen, that would be augmented reality. It is a virtual reality environment in which you can train on the method to use a fire extinguisher. So there will be like a virtual fire extinguisher, a virtual fire. There's a small training course where you learn how to operate the VR components, and then you can pick up the virtual fire extinguisher and fight a virtual fire in that environment. So you've got to go through the process like pulling the pin and making sure you grab the nozzle and checking your gauges and all that stuff, right? When you're outside it and looking at a screen, it doesn't quite give you the sense of depth and scale that you get because obviously with VR you get a full kind of 3D experience. So when you're dropped into the bottom of a blast furnace and you look up, it feels like you're looking 100 feet up in the air, right, at the top of the furnace, and you get this sense of scale that really kind of overwhelms you at times. I am a mechanical engineer by training, right? So I work more on the simulation modeling end of things. In terms of virtual reality and the integration, it's really just being able to show the data that you generate from a simulation in a very visual way. It's a lot easier to explain to someone that the natural gas combustion in their furnace is not working properly because we can see where the flame is and see that we're running out of oxygen in this area. Having a full 3D environment to work with, that shift from 10 years ago, 15 years ago to where we are now, taking the simulation tools and making them into this very kind of interactive, hands-on, realistic type thing has really helped in terms of being able to display the technical results. I got a PhD in mechanical engineering because I really like analyzing the physics of what's going on in things. And there's all these setups for equations and calculation models and reactions for chemistry and all this stuff that all get looped into the simulation model. And it's predicting what's going to happen in the real world based on a set of very detailed inputs that you give it. It's a very important kind of tool to focus on making sure that you put good inputs into your model and then being very careful about studying the outputs before you just start visualizing a whole bunch of stuff, right? Because you want to make sure it's correct. So we do a lot of work with validation. We compare with data measurements wherever we can, right? And it's not always available for the exact same points, but if you can get a general sense to compare, you can be reasonably confident that the model is going to predict in condition A or condition B what's going on. In the end, right, that's kind of the end goal of all of this, right? Something's not working right somewhere, and we're trying to fix it. But to be confident in fixing a $200 million capital process, you're not just going to change something and hope it works, right? You're going to run a computer simulation, and then you're going to test it and verify that that makes sense. You're going to test that on a small test rig, and then once you're confident, you're like, okay, now we make the change. Hopefully, it saves you a couple $1 million a year in operating costs, right?